pixels in that one. Seriously, that's what we do. Pixel by pixel, and you get a figure of merit. If the figure of merit is satisfactory, then that's our local view cell. Remember the one that recalibrates the odometric error, which then connects off to the pose cells and so forth. If you come across a scene that you haven't seen before, it doesn't match any of the templates you've seen before, create a full template and so on. Remarkably, such a simple process can achieve some very remarkable results. Okay, pose cells arranged in a hypertorus aren't very useful to do anything with. How do you read them? We use a process called developing an experience map. So remembering that local views can be aliased. We don't expect appearance, particularly when I'm just using 4 pixels, to be completely de-aliased. So it's going to be aliased. I need a de-aliasing process, and this is where the pose code and the local view work together. We look for unique combinations of pose code and local view working together, and we call that an experience. And an experience turns out to be, they turn out to be quite unique. Right? It gets rid of your aliasing problems when we're working at scale. And I'm talking over tens of thousands of templates, talking robots working over weeks, I'm talking mapping kilometres of road, all of these kind of things. So an experience that is a unique combination of the pose cells and the landmark cues. When we string experiences together, if either of the local view or the pose code changes, we create a new experience, we keep some kind of link between them. We're not neural anymore here, I might point out. We're really just using a more conventional, topological data structure. And, of course, you can do all the nice things of building a graph. If you close the loop, in other words, you come back to the same experience that has the same pose code and the same local view, then you can start to do all of your nice graph relaxation techniques to build up a pretty good map, a pretty good global map that's actually human readable to some extent, and it's useful for path planning. So, what do we do with it? So here, we basically strapped a MacBook on top of Michael's car, and we went for a drive around the suburb of St. Lucia. So that's the video you're seeing up on the right. Obviously, we didn't drive that fast. The video just sped up. The route that we took this is the initial study, which has a reasonably short video attached to it, is up on the left there. And what you can see is the experience map coming together. So I've got local view being pulled out of the scene at the top right. I'm actually extracting the odometry information from that camera. There's no GPS here. Right? There's no other input other than that video feed. That is the only thing driving this whole algorithm. So I'm getting my odometry from that camera, I'm getting the local view from that camera, I'm running it through the algorithm, and I'm pulling out an experience map that looks like that. It shows many of the metric features, and it's certainly got the right topology. It's certainly now useful for path planning, it's certainly useful for navigation in terms of what we want to be able to do. We extended that study out to be the whole suburb, 66 kilometres of road, 100 minutes of webcam video. And running this through the algorithm, it does it in real time. It all runs in real time. There's no repeated training or anything here, it's one-shot learning. It very quickly generates these things. So, okay, I'm at an indoor positioning conference here. What's this outdoor stuff? Well, obviously what I've just shown you, I'm not using any of the usual outdoor tricks, I'm using GPS. So what have we done indoors? Indoors, we took on this idea of an office delivery challenge. Let's think about the robot we want in the future, coming into our house, we get it out of the box and switch it on. We don't want to have to train it or feed it out of our house. We want it to learn. So the idea here is we've got a robot that started blank slate in our office and lab complex, and we asked it to do 1,000 deliveries over a 2-week period, all times of night and day. So we were doing changing appearance, all kinds of things. It maintained its batteries by locating and docking with its charger. Halfway through the study, at the end of the study actually, we kidnapped it and took it to a complete new building, where it had to realise that the environment was different. We didn't tell it it had gone to another building. and it started mapping again. Built a new map, not connected to the old map. Did some deliveries over there on locations that we gave it, took it back to the original place, it kept going. Right, so this is a pretty challenging robot task, a pretty challenging indoor positioning task, and indoor navigation task. The study was conducted across these two buildings, so level 5, the Axon building, and level 5, incidentally, of the general purpose South building. And so they're reasonable sized environments. And you can see the red circles are our delivery locations, the green circle is where the battery charger was. This is the robot doing its thing, waking up off the battery charger and doing a little bit of localization. It now gets a command to go to goal 5. All the computations being performed on board. Requests are coming on internet, and now it's navigating to goal 5. For health and safety reasons, again, the robot traveled much slower, the video sped up. When it reached goal 5, there we go, it uses Arnold Schwarzenegger's voice to tell us that it has, in fact, completed its goal. So, over the 2-week period, it failed once. 1,177 out of 1,178 deliveries of that nature. And one time it failed, I blame undergrads for throwing their bags across the hallway and making it unable to actually navigate. And it failed gracefully. After 5 minutes its gate up. Reported it was unable to do the delivery and went on to the next one. It didn't increase its delivery times, its computation times. Space plateaued out in the initial environment. It grew, of course, when it went to the new environment. And then obviously it did the recovering from kidnapping. So we're not just talking about playing around with rat brains here. There was some actual real robotic stuff that followed on from this, which are some very pleasing results. All right, so obviously I can go home and get some rest now. I've solved all the problems. Not quite. There is, of course, a big downside to all of this. Even though we've got this nice robust system that performs well, there are around 20 parameters there that are magic numbers. Truly the only person on the planet who knows how to make them work just right is Michael. I have some idea, but really Michael's the only one who can put the correct combination of 20 together. This isn't good. Now, it's true that you can go from one app to another without having to change these a lot, but if you want good performance, this isn't the way that I like to work as an engineer. I want to get rid of the magic numbers. I want to come back to some units that I understand. So, from that point of view, we evolved the system. We went from RatSLAM to CatSLAM. No cats were harmed in the making of this algorithm. CatSLAM comes from an acronym for Continuous Appearance-Based Trajectory SLAM. Yes, it did take a few cups of coffee for us to get that algorithm out. And the key idea here is that we're keeping the key data structure as a trajectory. We're using appearance-based matching, but we're treating trajectories as a continuous data structure rather than a sample data structure. The nice thing is we get rid of the magic numbers. So let's consider, just to quickly explain CatSLAM, a robot that's just doing its usual thing. It's closing a loop. It's going around in a circle, some topology, simple topology, and it's closing a loop. When I create a trajectory, whatever kind of system we're using with our digital techniques, we've got a sample. And in fact, even rats, to some extent, it seems that they make samples of the environment. Sampling seems to be quite natural here. But importantly, when we create a trajectory, we not only keep the samples, but we assume that the piecewise and linear components of the trajectory in between the samples is also part of the trajectory. We consider the whole trajectory that we can sample at any point. So it in fact becomes continuous. So the process then of performing matching with a continuous trajectory, if we start moving our trajectory along, as we start to gather new samples, we're constantly comparing the likelihood of it matching not just against previous samples, but across the whole trajectory. Now this is an important part, this is an important lesson from RatSLAM. RatSLAM, with its kind of fuzzy activity packets, one of the things that we really picked up that it was doing, one was that it wasn't interested in building nice graphy type maps, that it was keeping these trajectories, and two, it had the ability always to interpolate. So this is what CATSLAM does. We're building a trajectory that's much more familiar in an engineering sense, but we're really keeping track of what goes on between the samples. We can measure likelihood of being in the same place. We use the same sort of techniques that Oxford use in their FatMap algorithm. And we keep track of the likelihood of being back at a place I've been before, and independently the likelihood of this in fact being in a new place. So as the robot continues around the trajectory, at some point when it closes the loop, gets back to the beginning, we're going to see some sort of distribution, not necessarily along at each sample point, but also along the linear stretch in between. And that becomes very important in doing all of this robustly. And at this point, the likelihood of being in the same place exceeds the likelihood of being in a new place. We've got a great candidate now for loop closure. So how do we do that? The way that we compute it, and we're starting to think that there may be better ways to compute it. The way that we've been computing it is by using a particle filter across that trajectory. So we're taking some random samples along that trajectory, not necessarily at our sample points, but where we choose to have the particles at any point, indicated in blue. We can use appearance-based measures, and I'll talk about how you interpolate appearance between 2 points in just a minute. We can take appearance-based measures to give each of those particles a score. How close is it to the likely appearance of that place? When the robot moves, so we've added to the trajectory, we move each of the particles in the same way. And those particles might move to somewhere that's near the trajectory, or they might move somewhere that's far from the trajectory in both space and orientation. If we then bring those particles back on the trajectory, you'll see we update their score. The ones that had to move a bit or a lot have their scores reduced. Those that are fit the trajectory keep their scores much the same. And now this is behaving like the filtering properties of the pose cells in RatSLAM. We have this odometric filter of a sequence of movements over time. It doesn't match the kind of movements that we've done in the past, and which is an important property of RatSLAM. So now we've got a good way of scoring a new particles repeat cycle. Update appearance, repeat cycle, and so forth. Okay, so how do you do this matching in between 2 points? With CATSLAM, as I said, we based it on the FatMap algorithm from Oxford. The FatMap algorithm at its simplest gets a collection of surf or sift features for the different sample points. I've labelled them with convenient names here, but I think we all know the kind of processing tools I'm talking about here. So let's suppose I have a set of features at one sample point, a set of features at another sample point. If I see a bunch of features that are in common at the place that I'm trying to match, then this is probably going to be a good match. And there are a nice set of Bayesian calculations we can do to work out how good that match is. If on the other hand I see a set of features that are quite different, then this is going to be a poor. And I can assess all this in a Bayesian sense. I can do more. If I'm building these trajectories and I have locations that can be easily geometrically interpolated, and can also be interpolated very clearly from reference images on either side, I can get rid of them. And I can do some very effective pruning. And in fact, I can always come up with a figure of merit for whether an individual sample should be pruned from the network or not. So I can cap my memory requirements if I want. We compared ourselves then to the FatMap algorithm. We've used them as the kind of front end. We wanted to see that as we added CATSLAM, did it in fact improve what they did. FatMap is based, has been principally assessed around this New College data set at New College Oxford. The blue line is the FatMap results. Now the FatMap results are pretty astounding, right? In terms of a precision recall curve, so in other words, at let's say 50% recall. In other words, 50% of the time, in fact, that algorithm knows where it is. It's right 94% of the time. That's a pretty good PR curve for something that's just working off camera. When we added RatSLAM, when we added this notion of pose filtering, stuff that we learned from RatSLAM, we immediately boosted the performance of the algorithm. And you can see that the difference between the green and red curves there, the green curve used less particles for sampling and had some fairly harsh pruning in terms of the number of nodes that we had. But it didn't degrade so much. You can go further than this if you actually address the notion of loop closure and build that notion into your trajectory and say that if these 2 points are the same, you can perform loop closure only in a local sense. We don't make any claims of global metricity here. Global metricity is not important in forming a topology. We're interested in knowing where we are, not in terms of a topology, not where we are in XY space necessarily. The two things are quite different. So in terms of creating a graph, we now have a set of nodes. We can run the algorithm in much the same kind of way, and we can boost the performance yet again. Right? We can collapse our network even tighter. We can use less samples, and we can really start pushing out to the right-hand corner of that precision recall curve with quite a reasonable number of nodes. If we go indoors then, and this is some work that was presented at IROS just a few weeks ago, we went back to our pioneer robots wandering around a building at QUT. We had a very strong ground truth here based on some lasers and some external nodes. And what we were able to show that as we ran different routes over a 7-day period using our pioneer robot, that we were able to get very good localization. We were able to get very good delivery style performance again. The interesting thing in terms of looking at a precision recall graph here is that if you use FatMap, a state-of-the-art appearance-based matching algorithm, its performance degraded over time. Okay, so day 1, FatMap's doing reasonably well. Day 3, day 5, day 7. And by the nature of the algorithm, you'd expect it to degrade. Cat graph, on the other hand, and RatSLAM, I would say, would likely be the same. Cat graph, on the other hand, as we continue to build this network and make the connections, actually improved its performance over time. And you can see the trend towards improving performance as it heads out towards that right-hand corner. So this is where we've gone to from RatRam. We've now got a nice engineered product where you can actually look at real values. You don't have to worry about neural networks. We can use all of the kind of maths that we're familiar with. But there are some new concepts here. There are some very new concepts in terms of the way that we use trajectories, that we're not so concerned with global metricity, that we're more interested in local connectedness, the way that we use filtering in a continuous sense. All these things we've learned from rat brains enables us to get a little bit closer to the kind of performance that we see with rats. So in conclusion, understanding the biological basis of rodent navigation, and I hope I've been able to explain a little bit of that to you today, has helped us create a very highly competent robot navigation system performing near state-of-the-art in terms of the kind of tasks that we showed you there. The evolution, RatSLAM and CatGraph now is a nice engineering style product that we're taking on further. We're doing continuous work now to see if we can get this algorithm to work over months with cat space and computation requirements. I need to acknowledge Michael, who did a lot of work on the RatSLAM algorithm, and Will, and a cast of at least dozens with various collaborators as we worked on this. And of course, acknowledge the ARC for their generous funding over the years of this work. Thanks very much for your attention.
Thank you, Gordon. That's an extremely interesting presentation. Do we have any questions?
100 pixels for the indoor robot, which you mentioned? Or did you?
128.
Really?
For the indoor robot was 128. I should have kept the slide in to show you how it was done. The 128 pixels were picked out of it was the most interesting part of the omnidirectional image. Carpet, pretty boring. Ceiling, pretty boring. So taking the middle strip out of the omnidirectional image, performing histogram equalization on that image so that you've got a nice range of values to use. And then turning that into, subsampling that down into 128 pixels. We did do lens correction on it as well so that it looked like a wraparound style image, not the raw omnidirectional camera image. And we used sum of absolute differences. We took the difference between each pixel, took the absolute value, added it up. That was our figure of merit.
Thank you. It's very interesting.
We've played around with a number of very cheap ways of matching images. Michael has gone on now to get a Discovery Early Career Award, which is one of the ARC awards, a DECRA in Australian terms, where he is now looking at how few pixels can be used. We put a paper into the last ICRA, and I didn't present it here because it's really Michael's work, probably more so than my own, where we were able to use some of these appearance-based image processing techniques, the global descriptor, if you like, rather than features, to do the outdoor driving around camera thing again. But what Michael showed was that he could drive along the road during a sunny day, and then he did it again during a storm at night. Right? So he did it on a sunny day, and he did it again during a storm at night. And what he showed was he can make them match. He can line up those two sets of video that this is the way that it works, and perform localization for sunny days and stormy nights. And that's in fact the title of his DECRA. Localization for sunny days and stormy nights. And it's really interesting using this idea of sequences, using this idea of global descriptors rather than jumping to sift and surf and how do I deal with bags of words and that kind of stuff. Using these appearance-based things, you get some remarkable results. The other one that he's done is the big racetrack in Germany, very famous, very long one. People particularly like riding motorbikes around. Yeah, well, something. The fans of motorsport will know what I mean. People love jumping on this racetrack and strapping a GoPro onto their helmet or onto their dashboard and putting it up on YouTube. My lap. So what Michael's done is he's actually downloaded all these YouTube videos from completely different cameras. No calibration. Right? No idea what the camera specs were. And he can match their laps. He can compare these two different, which bit were they faster and slower on, and actually compare different people's laps just straight from their YouTube videos. Again, using the same sort of principles we're talking about.
Once again, so the robot which is running around the building actually does not exactly know its pose. Its coordinates actually just knows the location where it is. Is that the case?
And that's the biggest lesson we learned from rats. That is the biggest. Yes, there's a notion that has cells that say I'm at X, Y, theta, but there's no coordinate frame here, right? They don't carry a coordinate frame. They certainly don't put features into a coordinate frame. Everything we understand as engineers coming into this space, we go, if you want to do localization and mapping, you need to have a coordinate frame and you need to put features into a coordinate frame. No, you don't. None of this work puts features into a coordinate frame. No, we don't keep any features of the world in a coordinate frame. Everything's in a topology. There is useful metric information in a local sense. How are different experiences connected? In a global sense, it's not so important.
Okay, so that would exactly be the next question. So the robot approaches, say, position A, and then he has to do something. Then it's important that you really can approach in the right direction, at the right position. But Does the system then switch, or is it still down? Or is there somehow a transition to local? I don't know how you make it.
Yeah, so it is, you're exactly right. It's a hybrid system where you use the topology to get to a position where the robot should be able to see the delivery point. Right? Once the robot can see the delivery point and it gets that cue, then it moves into a visual servoing mode. And simply visually servos in using well understood visual servoing technique. You don't need to know where you are in a global frame, you need to know where you are with respect to the place you're trying to go. Or, in fact, a lot of the visual servoing we do image-based visual servoing. So we don't have a global reference frame there, right?
How do you think that rats do in open spaces? I mean, and not roads or
Yep. So rats generally stay out of open spaces because they get eaten. They're evolved to work in feature-rich environments. They're also remembering that they're using olfaction and that they're using whisking for a lot of their information as well. And in that respect, in open spaces, they cheat. Because does anyone here own rodents? You'd be familiar with the smell if you do. Because rodents, it's not that they're dirty creatures, it's just that they're constantly leaving little reminders of where they've been. Post-it notes, if you like. Olfactory post-it notes. I've been here. And what's more, their post-it note has information about what was I doing when I was here, you know, what other rats have I been where, what mood was I in. You know, they're little excretions that they make as they go along help them. So in open spaces, when rats navigate, they'll be leaving themselves olfactory cues to help themselves get back as well and be using that information. The olfactory cues are not unique though, right? They will keep the rat to a path within an open space. So there's a lot of this work that is in fact predicated on the notion that you have some behaviours, the same as we have behaviours for delivery, we've also got behaviours in the robot that keep it to a path, that make it likely to repeat in the same places, just as a rat does. Now, yeah, you could argue that that's another limitation on the system, and we're doing some work around that at the moment. But yes, this path-based navigation is an important property of the system. Excellent question.
So I have a question about, it is important to us that the creators will try to distinguish one floor to the other, these multi-level buildings, because the building structure is very similar. Would you expect the robot to get confused if you kidnap the robot to the next floor?
No. So the thing about topologies, right, is even though they might occupy the same XY space, they don't get connected based on global electricity. They never get connected based on global electricity. So even if you're keeping purely an XY map with these topologies, as you move from floor to floor, the only place that they'll connect is in the lift door. We've done that.
No, I think because of the building structure being very similar from one floor to the next.
Oh, in terms of aliasing? Again, it's a matter of the connection between the space. How does the robot make the connection? If you had very similar appearance from one floor to another, turns out the buildings we've worked in, we haven't come across this problem. It's an interesting thing to do. If you had a building very similar in appearance between the two floors, yeah, I expect that this algorithm could very well get confused. And you would need to have features that could disambiguate between those two floors. So the data structure can handle, the algorithm might get confused, and you know, I think that as we all might, you know, if we couldn't read the numbers and the names on the door and so forth. We're actually doing some work where we're putting text and using text as one of our features, but that's a slightly different direction too. Yeah, good point though.
Good, thank you very much, and thank you very much for those questions, and I'd like to again thank Gordon for his presentation. After the break, adjourn into 4 parallel sessions, A, B, C, D.